It's Tuesday, April 16th in Cambridge, Massachusetts. And we're very pleased today to have Dolev Bluvstein. He was an undergraduate at UCSB and now is a graduate student in the group of Misha Lukin at Harvard. He's done very exciting experimental work on quantum information and quantum computing. He's going to tell us about logical quantum processor based on reconfigurable atom arrays. So Dolev, the floor is yours.
Okay, thank you so much, Arthur. Okay, let me share a screen. Yeah, just need to... Okay. Okay. All right. Thank you so much. So indeed, I will tell you about our recent work in the Lukin group, working on quantum error correction using arrays of neutral atoms. This is, I'm hoping questions during the talk will slow me down, and so I won't just ramble. So even though I think a lot of the audience is going to watch online later, I would actually love if you interrupted with questions, especially about the more conceptual things. So, starting off broadly, I do experimental science, and in particular, experimental quantum information. And the past decade has been quite exciting. In the 2010s, that's around the time where people started to use physical qubit systems to do a variety of interesting explorations in quantum computing. And when I say physical qubits, I mean things like ions, defects, atoms, or superconducting qubits, things such as like individual particles that have two-level systems. And we've been able to use these to study a variety of interesting kind of applications in quantum information. And recently, our size and control over these systems has gotten so developed that we can now really start to use these as scientific tools to try to really probe quantum mechanics and quantum many-body physics and study quantum mechanics in a regime that we can't simulate classically. And that's been one very exciting frontier. Another frontier, which is what I will tell you about today, is that of so-called quantum error correction, which is that now we can take these physical qubits, these individual two-level systems, and then start to entangle them into conglomerate qubits that we call logical qubits. These are error-corrected qubits made up of entangled physical qubits that now can be protected and can have lower error. And this is actually very important, and this is going to be the focus of today's talk, is quantum error correction. And in fact, in our large-scale attempt and our large-scale quest to be able to build a large quantum computer, fighting decoherence is the central challenge, the central obstacle to using quantum mechanics for computation. And quantum error correction is, to date, the only known realistic route that we have in order to get the operation errors or the gate errors from what our physical qubits can do at the scale of 10 to the minus 3 down to what we need for doing useful algorithms at the scale of 10 to the minus 10 and below. This is to date the only way that we actually know to get to this scale. And actually, this is so dramatic that before quantum error correction was invented, people thought that quantum computing would be just fundamentally impossible because of this kind of dramatic difference between these scales. And again, please interrupt with questions if there are any during the talk. So again, this is a talk about quantum error correction. And yeah, please.
Yeah, so typically, if I don't have this error correction method, how small an error rate we can get if we just prepare a very, very good qubit or something?
That's a very good question. So, and maybe another question implicit in that is how sure are we that we need quantum error correction? So the best physical qubits we have to date can be on the scale of 10 to the minus 3 error rate. And we could expect that they'll get to 10 to the minus 4, maybe 10 to the minus 5. But we're really not expecting, for some algorithms, we need to get to 10 to the minus 14. We really don't expect that this is possible. And actually, there's many interesting historical accounts here. So actually, just coming into some history of the field, because this is nice in this intro slide. So, for example, when Peter Shor first came up with a factoring algorithm, there was a lot of excitement, but there was also a lot of skepticism. People actually really reminded them of analog classical computers, which are actually also very powerful. But the reason we don't use analog classical computers is because they can't be corrected. And there's no digitization that kind of can allow you to kind of snap onto one state or the other, like you have with a bit that can be 0 or 1. And actually, so it's a pretty fundamental thing that you need some type of digitization and some type of error correction to do large-scale computation of any sort. So if that kind of makes sense. So, okay, to answer in two parts, no, from a technical perspective, we don't believe that we can make the physical qubits this good. And also from a theoretical perspective, if you don't have any kind of intrinsic redundancy or intrinsic error correction, then, just generally, modes of computation become not robust, if that makes sense. Yeah.
I know in classical error correction, it's often like the majority vote, like
Right.
1-0, like that.
Yeah,
But here, obviously, because of net something we can't make.
that's right.
3 copies of the same state. Is it a fundamentally new like way of approaching
It
or
is. That is a perfect segue to the next slide. Okay, fantastic. So, okay, you perfectly segued me. In case someone couldn't hear the question was, classical error correction works by copying bits, but in quantum error correction, is it actually just a radically different physical origin? And the answer is yes. So, so classical error correction has been known, at least, in its primitive stages for millennia, right? Like you can take a bit and then copy it many times. Now, for example, if we take a bit 0 and we copy it to 0, 0, 0, if one of the bits fails and the last one, for example, flips to 0, 0, 1, then we can do majority voting by just measuring all of our bits and seeing that that one is the one that had the error, and in that way return to our original state and remove the error. So that's how classical error correction works. But quantum error correction actually has conceptual challenges, and it actually is a physically different type of mechanism. So, one is the one that you had correctly mentioned, is this no cloning theorem. We can't copy quantum information, so we can't take a state psi and then copy it 3 times, for example. That already kind of, makes us concerned that quantum error correction is not possible. The other issue is that how do you even check for an error without collapsing the state? We know with quantum mechanics, when we measure things, they collapse. We collapse our superposition. So how would you even measure this bit in order to see if it had an error? So for these 2 reasons, people were actually, coming back to the history of the field, people were, 1, concerned that to be actually different than like analog classical computation, you would need to be able to do quantum error correction. But, and just to work, you would need to do quantum error correction. But people also had, fundamental reasons to believe, from these 2 reasons, that you actually could not physically do quantum error correction. And it was actually a remarkable theoretical breakthrough from Shor in 95, and then shortly followed by others like Steen, that shows that quantum error correction is physically possible. And the physical underlying mechanism that it utilizes is that now what we do is we don't copy a bit. We take a logical qubit that we care about, something we're trying to protect, and then we use entanglement to delocalize it across many individual physical qubits. So we take this one logical qubit we care about, and then we use entanglement to spread it out. And now it's actually hidden. It's so hidden that now if the environment comes in and the environment measures, for example, this one physical qubit, actually will learn nothing about the underlying state that was stored. And that's how quantum error correction works. It uses entanglement to hide information so that the environment can't access it. And by being delocalized, it becomes hard to accidentally reveal the state of this logical qubit or to accidentally manipulate it. So that's how it's robust. And in order to actually detect errors that happen on our qubits so that we can, remove errors from the physical qubits and preserve our pristine logical qubit state, it turns out that although we can't measure individual physical qubits, what we can do is we can measure their products. And by measuring the products, we actually don't reveal what state we're in, but we actually are able to still reveal the presence of local errors. And these products are these so-called checks or stabilizers that we measure in a quantum error correction code. Okay, let me take a pause and see if there are any more like high-level questions here. The talk will procedurally get more advanced.
How does the error correction depend upon the number of qubits?
Oh, okay, great. That'll be the next slide. Okay, you can ask perfect questions. Okay, so I'll give an example here on the next slide. So first I'll introduce this Tor code in order to answer your question. So a quintessential example of these quantum error correcting codes, and one of the still leading error correcting codes today, depending on what metric you're interested in, is that of the so-called Tor code or surface code, and invented by Kitaev in '97. And what this logical qubit looks like here is its error-free state is given by the simultaneous eigenstates where of all of these x and z stabilizer products or checks being simultaneously equal to +1. So in this state where all these mutually commuting operators is +1 is our logical code space. And in this state, we can just read off the logical state by looking at these vertically and horizontally propagating x and z logical strings. And we can use this to just read off the state of the logical qubit when we have no errors in this configuration where all the checks are satisfied. And now what this looks like is if we have a physical qubit error, for example, on this qubit, that we have a bit flip error, it'll anti-commute with these 2 z checks. And so actually, without revealing the state of the underlying system, we're not actually measuring the individual qubit states. We're only measuring the products. We can, because it anti-commutes with these 2 z checks, we'll see that actually this qubit had an error. We infer that. This inference process we call decoding by looking at all of our checks and inferring what errors happen to the system. And then after we infer this, we can undo it, either in hardware or actually we can just keep track of it in our brain. And as our lattice size or our code distance d increases, we get more opportunities for errors because we just have a larger system. but we also get more checks. And this leads to a threshold behavior. And now coming back to Arthur's question, in principle, if the errors in our system are below some characteristic threshold, then now as we increase the size of the code, we can actually exponentially suppress the logical error probability as we increase the code distance d. And actually, it turns out for this surface code or toric code, it's actually quite favorable. These local error densities that we need to get to are only at the scale of 1%, which modern hardware is readily able to do. And this now starts to offer us a realistic route to get to extremely small errors, where we can get to 10 to the minus 10 errors or so by having several hundred qubits that are a factor of 10 below this threshold, and then just exponentially suppressing by making this lattice size bigger. So this is now looking way more promising in order to get to this 10 to the minus 14 scale of errors that we need. And I was not alive at the time, but it is at least my understanding from history that it was this theoretical breakthrough of quantum error correction that really allowed this field of quantum computing to take off, because it showed people that actually you can really build these devices and you can really kind of correct errors in these systems. And moreover, although we've learned so much doing computation with physical qubits in the lab, it has been understood since essentially the beginning of the field that eventually we're going to need to switch to doing all of our quantum computations and quantum algorithms with error correcting qubits in order to be able to get to doing programmable and robust quantum computations. Let me take a quick pause here. Okay, fantastic. Okay, but there's also challenges. So, it's quite promising, but, as we mentioned, now we need, several hundred qubits in order to make one very good error-corrected qubit. And this now starts to lead to pretty enormous, qubit and kind of resources that we need in order to do large-scale computations. And if you look at optimistic estimates that we have in mind for doing large-scale problems, we're imagining things like, millions of physical qubits and logical qubits that get down to errors of, 10 to the minus 10. And, not only are these large system sizes, but this is actually greatly further compounded by the central challenge of efficient classical control of these quantum systems. And from a technical experimental perspective, this will be really the central message of today's talk in terms of, all the experimental things to take away is efficient classical control. In classical computers, something that, classical computing architecture people have gotten really good at doing is using something like 1,000 wires in order to control billions of bits in a computer. But in a lot of the quantum architectures that we've built to date, they're always built by this way that we go, several wires per qubit. So each new qubit that you add several new wires to control it. And now if you have millions of qubits that you need to control, you need to have millions of different individual control channels that you're controlling simultaneously. And this is something that's not quite practical. So although error correction is so exciting, there's two really key challenges. One is the so-called wire problem, which poses a significant challenge to doing large-scale control over all these qubits. And another challenge is that, we talked about how we delocalize this logical qubit and we hide it, and this makes it hard to accidentally manipulate. But unfortunately, it also makes it hard to intentionally manipulate this logical qubit, and now it becomes hard to do operations on it. And these large overheads, combined with the complexity of actually doing operations on logical qubits, have so far limited studies in the field to, 1, 2, or maybe 3 logical qubits in operations. Okay, any questions? Yeah, please.
Like if you have, like, for example, like a common computer, right? You have like working memory.
Yeah.
You're able to access things like you're using.
Yeah.
If everything is delocalized, would there be like a even larger problem in accessing like larger sets of like complex data that would be or information that would be stored?
It really depends on the architecture. So actually, this is one slide I took out of today's talk. So here, let me skip forward and say that. So we made, for example, in this work up to 40 error correcting qubits or 48. And one of the ways that we did that here is we actually used, very inspired from classical computing architectures, we actually had a storage region and a computation region, and we only operate on some small number of our qubits at a time, and then we store them back in the CPU. But what back in the RAM kind of? So in a sense, we are using that multiplexing and that zoning in order to be able to more efficiently control the system. But there's a catch, which is that what you said is correct, that we're delocalizing this information, so now it becomes more hard to operate on. And so a big difference is that, in classical computers, we operate on bits, and bits are these inherently protected, digitized degrees of freedom. In quantum computers, the inherently protected, digitized degree of freedom is the logical qubit. And so the theme of today's talk will be building a processor where the logical qubits are the fundamental units. So when we do that kind of zoned architecture, it's all happening on the logical qubit level. And the logical qubit is now the fundamental unit of the processor.
Can I ask a follow-up?
Yeah.
For example, if you have an operation in RAM, for example, clearing memory,
Mhm.
and in your working memory, so you can put new things in.
Yeah.
Do these logical qubits survive whatever physical analog would be of clearing the memory?
So it depends on what exactly you want to do. So if the clearing the memory means measuring everything, and resetting it to qubit state 0, that is definitely something that you can do with logical qubits or with physical qubits. Yeah, it depends. There's different types of analogies to, for example, what people call QRAM. And this is a broad topic that people don't even necessarily agree on what QRAM is, other than it's a fun concept to define and think about. And that is, it kind of has different challenges depending on how exactly you want to store this information. But yeah, I don't know if that kind of answers your question. Yeah. It's a complex problem on a whole large architectural scale. What's the best way to do everything? Yeah, absolutely. Okay, fantastic. Thanks so much for the questions. Okay, I think this was a nice kind of high-level overview. Okay, so there's some big challenges, and I'll tell you today about our recent approaches to solving them. And it's using these new tool that we've developed known as these reconfigurable atom arrays. And what this looks like is we have neutral atoms that are trapped inside of optical tweezers. These optical tweezers are tightly focused beams of light shining into a vacuum chamber. Each tightly focused laser beam or tweezer captures exactly one atom. And now these atoms are stored in our processor, for example, in multiple zones. We store coherence in this nice long-lived, what we call hyperfine qubit. It's a magnetically insensitive state inside the atom that can live for long times in our system on the scale of seconds. And then when we want to entangle qubits for doing quantum operations between them, we very quickly zap them to these so-called Rydberg states. We use another laser beam, and this excites the atoms into this really high line orbital state where the electron orbit gets very large. And this now gets two atoms to interact. We quickly go through this Rydberg state, and then we store our information in this nice long-lived non-interacting hyperfine qubit state. And in fact, the coherence in this system is so long that we can move the qubits around in the middle of the computation. And this gives us two really big features. These will be the central takeaways from today's talk. One is it gives us non-local connectivity, which for quantum error correction turns out is extremely powerful. And two, it gives us this ability to now do parallel and efficient classical control, where we only have, a few wires in order to control this whole system, as opposed to having, a few wires per qubit. So those are really the two kind of salient features.
So I have a couple of questions. First,
Please.
You drew the picture two-dimensional.
Yeah.
Is that actually the way the experiment's done?
So the experiment is actually in 2 dimensions, and we could in principle do 3D, but 2D is always most natural because we live in a 3D world and you need one dimension to access things from.
And you talked about wires. Do you mean lasers?
Yeah, by wires, I mean a kind of abstract control channel. But yeah, here the way that it interacts with the atoms is lasers. Yeah, that's right. Yeah.
So you say non-local, like how non-local can you get? Can it be arbitrarily off-wall or?
Yeah. So any qubit can connect with any other qubit because we have these 2 qubits in the array, and we can, for example, move this one all the way over there, entangle it with some other one, and then move it back or move it wherever. So the qubits can move around during the computation, and we can entangle any 2. Great. Okay, fantastic. Okay, and then so, before going further, I want to just kind of heavily acknowledge all the amazing progress that has been done across the field. So actually, we learned a ton from looking how trapped ion and superconducting qubit systems were able to develop their systems. And, when we're sitting in the lab late at night, thinking about how we want to set up our quantum computer, we're looking at how, previous generations of experimentalists have built different types of quantum computers. And there's a lot to learn from that. Also, we're learning a ton from this kind of cold atom community that has done a lot of progress in the past few decades controlling large-scale systems. So we're really leveraging a lot from this previous works. Okay, so now I'll go into the kind of more technical part of the talk. So first, I'll tell you about how we program a quantum circuit with neutral atoms. I might kind of skip over some of the technical experimental stuff here, but please feel free to ask questions if there are any. And then I'll tell you more about our recent experiments doing error-corrected quantum processing. Okay, so from an experimental perspective, the one very central takeaway to remember is that of efficient classical control, and I'll say it about 100 times in the next 5 minutes. So, every time we start our experiment, we make a cold MOT of atoms. This is using standard atomic physics techniques, and this is, a picture from our lab. Our lab's MOT is not impressive by any means. We have roughly 10 million atoms in a millimeter-sized region of space. People, again, have been routinely doing this for decades. But what it makes it very clear is that cold and identical neutral atom qubits are essentially unlimited. There's a ton of identical cold rubidium atoms inside of this cloud. That's not the challenge. The challenge is how to control them all. And that's, set up in our experiment from the very beginning in terms of how we even trap our atoms. So for example, to trap large grids of atoms, we don't have 1,000 independently controllable laser beams. We have one laser beam that goes on one optical device that we call a spatial light modulator. It gets focused inside of our vacuum chamber where the atoms live. And then this spatial light modulator splits this one laser beam into 1,000 independent laser beams, each of which snags an atom with roughly 50% probability here. And then we take a literal camera picture of these atoms. And this is what, a real camera image is of our atomic system. And after we image them, we use another set of optical tools that's really important, which we call an acousto-optic deflector. And what this does is it uses two voltage waveforms. So there's two wires, and it utilizes frequency multiplexing. So each wire is containing, a complex waveform that has many different frequencies in it, in order to create rectangular grids of light that we can quickly program. And just with these two simple kind of global optical tools, we can now sort the system into defect-free grids. Here, like this square grid here, we can also do other fun things. Like here we made a Mario, where you can just sort these atoms into different configurations just by using, these simple global tools that are, again, multiplexed with this SLM and AOD. That's how we lay out our processor. In terms of entangling atoms, we use the so-called Rydberg state that I had mentioned. So atoms, for example, can be in either their orbital ground state or this orbital Rydberg state, which is this really high-lying quantum state that has this large orbital size. And what's really important about these Rydberg atoms is they get very large and they actually start to pick up a strong dipole-dipole interaction between themselves, or a van der Waals interaction. And it's so strong that if we put two atoms next to each other, then the interaction between them can be gigahertz if they're in the Rydberg state, which is a very large energy scale. And this leads to this phenomenon that we call Rydberg blockade, such that if we put two atoms next to each other in the ground state, and we simultaneously try to zap them into this, large orbital Rydberg state, they can't simultaneously get excited because there's a huge energy penalty for the state that's simultaneously excited. And so they'll simultaneously go into the superposition of Rydberg ground plus ground Rydberg, and they won't go to the state Rydberg. And just with that Rydberg blockade phenomenon, we can generate entanglement. Okay, so that's the kind of salient takeaway there. And we've been able to use this Rydberg blockade mechanism in order to do a variety of analog studies where what it looks like is we have atoms arranged into something like a Kagome lattice. We turn on our global Rydberg laser, and then we interact the system under this Rydberg blockade, and then we can study a variety of different dynamics that come out of the system. Digital evolution is more nuanced. We don't want to just, interact the system under its native evolution. We want to break down things into individual building blocks like single qubit and two qubit gates in order to do, universal quantum computation. And this is more nuanced and it has more degrees of freedom, but we still want to be able to do efficient classical control. This will really quickly glaze over, but an important development in the field, led by a graduate student in the lab at the time, Harry Levine, is that we can actually do a two qubit gate just using global control. I think I'll skip this. I think it's way too technical. But the really important takeaway is we can just put these atoms next to each other, zap this global laser. The atoms go through the Rydberg state and come back down. And just by using global pulses and using this blockade, if two atoms are next to each other, they entangle. And if they're not next to each other, they don't entangle. And we can now use this, digitization of, with this blockade in order to program complex circuits between the atoms. And this is the first quantum circuit that we ever did. It's making a 1D cluster state. Okay, so this is really important, so interrupt me if you're confused. So the way we make this 1D cluster state, we just put all the qubits in plus by doing a pi over 2 rotation. Then we do C, or a Hadamard. Then we do CZ gates on the links between the qubits, and we do this in just 2 steps. So we put the atoms next to each other, pulse our one global laser pulse, and now if atoms are next to each other in pairs, they entangle under this Rydberg blockade mechanism. Now we move half the system. We do this by just using one wire that controls the x positions of all the atoms. We do our second pulse of the global Rydberg laser, and these 2 parallel steps, we entangle these atoms into this 1D line. And that makes this 1D cluster state here that we can probe by looking at these 3-body operators, these stabilizers here. Okay, the really important takeaway with this reconfigurable atom array system, how do we program quantum circuits, is the position defines the gate through this blockade mechanism. And now the sufficient control that we have over these many qubit positions that, allowed us to, for example, make a Mario movie, now allows us to do and make, complex quantum circuits because the position defines the gate connectivity. Let me take a quick pause.
How does the measurement is done here?
So here we do it by doing a local rotation on every other atom, and then we projectively measure in the ZXZ basis. Yeah.
We go into the notion of next to each other. Is this some sort of XOR operation? How do you define next to each other?
For the gate.
Yeah.
Fantastic question. So for example, I'll describe the parameters used in our recent work. The blockade radius, which is the distance at which the interaction strength is the same as our Rabi frequency, is 4.3 microns. We put the atoms 2 microns apart. That puts them very comfortable within blockade. Ones that aren't interacting, we put them 10 microns apart. Yeah. Yeah.
What is the derivative of the in this configuration?
So it's like a entangle of the qubits after the gates.
What's the level of entanglement?
Yeah.
Well, it's a cluster state. So I don't know if that quite answers the question. So it's cluster state type entanglement. Yeah. Yeah. I mean, there's many different ways to analyze the entanglement in the state, but it's a cluster state. Yeah.
How does the blockade strength scale with the distance between the?
Great. The interaction strength is 1 over r to the 6th. So when we put the atoms like factor of 2 within blockade, they're very comfortably within blockade. When we put them like a factor of 2.5 outside of blockade, they're very comfortably not in blockade. Yeah. Great. Fantastic. Okay. So at the time, this was the first quantum circuit we ever ran. This is from 2022. At the time, how well we could do this was limited by how well we could entangle our individual physical qubits. That's something that we've recently improved a lot. So now we have, it sounds, technical, but we have, 99.5% probability of success every time we do a gate, or fidelity. That's actually really important because it's below this 1% error threshold that we talked about for the surface code. So that's one kind of big upgrade that we did last year. Another is that we can now do fully programmable single qubit gates across the entire array. And also we have ways that we can do measurement of some of the qubits in the middle of the circuit, and then conditional operations live during the circuit conditioned on the state that we measure. And that's really important for different aspects of quantum error correction. But I think I'll just glaze over these things, unless there's a question. Yeah, please.
So this is a two-qubit gate.
Yeah.
We have is there a similar mechanism for things like three-qubit gate, or is that?
Yeah, that's a really good question. So in this work, actually, so in figure 4, we do a CCZ gate using the blockade mechanism. Yeah, and there's also been really nice work from the Kaufman group recently doing up to like a 9-qubit GAG state by using global pulses. Yeah, so you can generate any symmetric diagonal entangling gate using this Rydberg blockade mechanism.
And how good is it?
So the CCZ is quite good. It's 98%. This was also like a very first attempt. That's already better than taking the CCZ and decomposing it into like individual CZs and local single qubit gates. So it actually works. It does work quite well. Yeah. Yes.
You said that the coherence time of the atom itself is like the hydrophile state is around like 2 seconds. But
That's right.
For mid-circuit, how long does the feed?
Great. So it's roughly 800 microseconds for the measurement of the atoms, and then the feed forward step of measuring, like 800 microseconds total, like for getting the data off the camera and then doing a conditioned operation. So 800 microseconds, still very short compared to our 2-second coherence time.
But does it have to go all the way through a computer to process?
It goes through an FPGA, so it's quite a bit faster. Yeah. Yeah. I mean, yeah. Yeah.
Yeah, when you mentioned this error rate, I have a confusion because this is actually a 2-qubit error rate. But when we talk about toric code, it's actually maybe modeled by the independent X error or Z.
That's right.
Yeah, so I think these are 2 different concepts. Here, this is some circuit error, and that.
Yeah, I swept a huge thing under the rug, but what I've told you is correct. But I did sweep something dramatic under the rug. So the density of errors that this toric code can handle in 2D in the specific way that I described earlier is 10%. For independent X and Z errors, and it's exactly the thing you described.
Yes.
The 2-qubit threshold is 1%, and the reason is twofold. One is that you actually have to do repeated measurements. This makes now actually you don't do a 2D matching problem, you do a 3D matching problem. That reduces the threshold from 10% to 4%. And also each node in your 3D matching problem has 4 2-qubit gates that it does, and that reduces the 4% to 1%. So they're disconnected but related in this way. Yeah. I swept that under the rug and you correctly picked up. Yeah. Okay, fantastic. Okay, let's talk about some quantum error correction. So, okay, so that's how we program circuits with our atoms. And now we're going to explore doing quantum error correction with these systems. So when we were doing our first work in 2022, we actually made this toric code on a torus by making periodic boundary conditions. And again, you can see here in this movie how we program the circuit. So we have 16 data qubits that are fixed in our SLM tweeters. And then we have these 8 ancilla atoms that are moving around the system in these rectangular grids. And there at that last step there, we made the periodic boundaries for this, torus. And every time we put the atoms into these new pairs, we pulse our global laser and it entangles these adjacent pairs of atoms. That's how we're programming the circuits here. And what we were observing in doing these first quantum circuits is that, really there's this amazing opportunity here that if we want to make the toric code larger, for example, it actually doesn't change the way we're controlling the system. We just add, more frequency tones in our frequency multiplexing and we make our laser bigger, but it doesn't actually make the control problem harder. Similarly, if we add more blocks of these error correcting qubits, then actually it still doesn't, increase the control problem. We're just making the system larger. And that's really central for what I'll show you in the rest of the talk, where we're going to be doing logical quantum processing. And here, the big observation that we had is that if we have, for example, an array of surface code logical qubits, the surface code is the same as the Tor code, essentially. Now, what this looks like is if we want to do a single qubit gate, not on physical qubits, but on logical qubits, then what it turns out that we don't have to do is a unique operation on each individual physical qubit of the block. For example, if we want to do a logical single qubit gate, all we have to do is effectively take one big beam that has the exact same light and exact same instruction and simultaneously illuminate all of the qubits of this block with this one big beam. And this is a gate that we call transversal. To do this gate on the logical level, you just do the exact same gate on all of the individual physical qubits of the block. And this really naturally multiplexes with optics, where we can effectively just take, a big beam and then treat this logical qubit as if it was one big atom. And that really simplifies the control problem for us. The other thing, however, which is even more important, is that we can also do this for 2-qubit gates. If we want to entangle two logical qubits, all we have to do is pick them up, interlace them by just moving these two grids past each other, pulse our one global laser, or one global entangling laser, and this simultaneously does a pairwise CZ between all of the physical qubits of these different blocks. And in this single parallel step, we can do a transversal entangling gate. And actually, if you look, for example, at Peter Shor's original paper describing how to do logical operations back from 1996, I don't think he meant easy from an experimental perspective, but this is exactly the way that people first envisioned doing logical operations before people came up with braiding and lattice surgery. It was to do things transversally by just doing bitwise, the same bitwise operation on all of the physical qubits that make up the block. And this now allows us to start exploring efficient and parallel computation, but with logical qubits. Does that kind of make sense? Are there any questions? This is super central. Okay. Yeah, please.
Is this a property of the surface code in general, like in particular, or is it a more general feature of any code that you can always do this?
So a lot of codes have transversal gates of many kind. The CSS codes, which are a huge family of codes, so surface codes, color codes, even these really complex LDPC codes that people study with like high dense encoding rates, they all have a transversal CNOT. So the transversal CNOT is among one of the most ubiquitous features, and they can all be realized in this parallel way.
But they're just, you can have other gates like non-Cliffords and so on.
You can have some non-Cliffords. We'll do that at the end of the talk. You can't have a universal transversal gate set, but you can have a universal parallel gate set. You need to do some measurement too. Yeah, parallelism is central with error correction. Yeah. You can't do everything transversally, but you can practically do everything in parallel. I don't know if that answers the question, but yeah. Okay, great. And I want to park on this transversal CNOT one more time because it's so central. So what we talked about is that, the way we're doing quantum error correction is we hide information by delocalizing it over these two blocks. But now if, these 2 degrees of freedom are hidden and they're next to each other on like a chip, for example, and we're trying to interact them, it's actually quite hard. So you have these 2 delocalized wave functions and they can't talk to each other. But what we can do is we can just take these 2 degrees of freedom and put them right on top of each other. And this greatly, simplifies, getting these 2 delocalized wave functions to interact by just doing this transversal CNOT. If we don't do this and we just try to interact things locally, we actually have to do techniques such as braiding or lattice surgery. And because these 2 things are delocalized over a separation of d, the lattice size, then you need to do something like d rounds of error correction or d operations in order to actually get these 2 degrees of freedom to entangle. When we do things transversally, we don't have to do that. It's inherently fault tolerant, so we don't require to do d rounds of correction between each logical operation. We also now can do long range and direct connections between logical qubits, which is also really important kind of from the perspective of having a large processor. And lastly, this property of having efficient control, all the physical qubits of the block act like one big atom, and we can do logical operations in this way. And using these techniques, we've been able to create our first generation logical processor where we're using these transversal gates. We're also utilizing zones inside of our processor. So logical qubits can be stored idly for long times without decohering inside of the storage zone, because our qubits have long coherence times. When we want to entangle 2 logical qubits, we can pick them up from the storage zone, move them into the entangling zone, and entangle them on demand. This is very similar to the kind of RAM concept we discussed. And also a readout zone where we can move some of our qubits away in the middle of the circuit and measure them in a time short enough such that the other qubits are not decohering. And that's kind of the basis of the experiments that we're talking about here. Okay? Any questions? Okay, so now I'll kind of overview some various quantum error correction experiments that we did with this machine. So one of the first things that you might want to do is see how you can generate entanglement between your 2 logical qubits, similar to how you would study entanglement between 2 physical qubits by making a highly entangled Bell state. Here we'll make a highly entangled logical Bell state. And we do this here by using surface codes. So we make here two distance 3 surface codes, meaning they're 3 by 3. We do state preparation by doing one round of stabilizer measurement. There's some important aspects here, but I think I'll skip over. I think they're too technical. We do one round of stabilizer measurement with ancillas, and then we move these ancillas away after we've used them for the stabilizer measurement, do the transversal CNOT. And here, what we're studying is, what we talked about for error correction. It's really important that we can improve operations as we increase the size of the code. Here, we're studying this, increasing the size of the code from distance 3 to distance 5 to distance 7. These are the largest codes that have ever been made, and also by far the largest surface codes entangled. The two largest surface codes previously entangled were two distance 2, so 2 by 2 codes. And what we can see by making these larger and larger codes is that we can actually improve how well we entangle these 2 degrees of freedom as we increase the size of the code. This is the first time that we're seeing that an entangling operation can be improved as a code size is increased, showing that the error correction can work better and better as we improve the size of this code. That's one really important bullet point. The other really important bullet point is that actually the way that we decode the logical qubits is very important. The way that we look at all the stabilizers and then infer what errors happened and undo the errors. And in particular, here we're utilizing this technique that we call correlated decoding that I'll tell you about a little bit, but it's actually really important for this experiment here. Okay, any questions? Okay. So here we're making a bell state between 2 surface code logical qubits. Here we're going to study other types of algorithms that we like to do with physical qubits, like making a large entangled cat state or GHZ state, all 0 plus all 1, but on the logical qubit level. We chose here to make this not with surface codes, but with color codes. Color codes are very similar to surface codes. They're topological error correction codes. They have more operations that are allowed. They can do the whole Clifford group. And here what we did is we made 10 of these. We used 5 of them to check for errors on the first 5. This is a step that we call Steen error correction. It improves how well we initialize these other 5 logical qubits to high fidelity. We move our ancilla logical qubits to storage, and then we make a GHZ state on 4 out of the 5 remaining qubits. And then by doing single qubit Clifford gates, we can measure them. And then here we look at our GHZ state fidelity. We can do other things that we're used to doing with physical qubits, like tomography, measuring the density matrix of this entangled state. Things that we're used to doing with physical qubits, but now doing them with logical qubits and understanding the various subtleties and challenges there. Here's a movie of what exactly this looks like. And again, these are real atom images. So we have these 10 blocks that are going to be our 10 color code logical qubits. And this first 3 steps, so 1, 2, 3, we make these 10 color code logical qubits. Then we do this 5 transversal CNOTs in parallel to check for errors. We drop off these logical qubits in the storage zone, pick up these 2 logical blocks, and then start to just slide them around the system and do these pairwise entangling gates, again, as originally envisioned by Shor, in order to realize these logical operations. Okay, any questions? Yeah.
Actually, I remember that in this paper, Shaw also claimed that the CCZ gate is easy to realize, but actually this is not.
No, so it's not that it's easy to realize, so he has to prepare some complex ancilla state. It's true in small codes, you can still kind of including the construction that he created. With small error correcting codes, non-Cliffords are still not that expensive. It's only when they get very large that it becomes really expensive to realize them.
Yes. Actually, I have a question regarding this experiment.
Yeah.
When you move the atom, how can you ensure that between the different rounds of measurement, there is no error? I think maybe you will have an error happen between that, and then your stored information will lose.
Oh, I think if I understand your question correctly, our coherence is quite long. So actually the decoherence between entangling operations is quite small. Does that answer your question? Or?
Yes.
Yeah, so the movement time is 200 microseconds, which is very short compared to the coherence time of 2 seconds.
Oh, okay.
Yeah. Okay. Yeah.
Is there any benefit in varying that time? Or
Oh, like doing it slower.
just having some times.
Of moving times.
Yeah.
There can be, yeah. So yeah, there can be. I mean, if you move faster, you have less decoherence, but also the system is faster, but you also have more loss because you're moving the atoms faster than their harmonic oscillator potential. So there's pros and cons. Yeah. Okay. So I'll delve into one of the really important theoretical lessons that we learned from doing these experiments with all these transversal operations. Actually in a collaboration with Arthur's group. So here, one of the things that we developed is this technique that we call correlated decoding. And what we do is we do these 2 transversal entangling gates, and they're fault tolerant. Fault tolerance here means that errors can't spread within the block because we're not doing any operations within the block. That's really important because now errors can't just uncontrollably build and create a logical error. However, errors can spread between blocks. If we do, for example, a transversal CNOT between these 2 surface code logical qubits, then an X error can propagate from the control onto the target, and a Z error can propagate from the target onto the control. So it's still fault tolerant, but errors do spread. And now if we make this like GHG state with our color codes, for example, then now a single physical X error that happened can look as if it was like a really high weight syndrome event, because the single X error on, for example, this top qubit here will spread to an error on the top qubit on all of the 4 qubits. And if we don't know about this, then it creates a lot of errors. But if we do know about our circuit structure, and we know about the correlations, it actually provides significant information when we see correlated events. So, one is that we can use this to improve our decoding performance. Actually, the way we came up with this correlated decoding technique, we were inspired by a type of error correction known as Steen error correction that actually intentionally utilizes this transversal CNOT in order to extract errors from the system. So it can use to improve decoding performance. It can also undo the error propagation that happened in the system by tracking everything that happened. And the way that we're doing this mathematically is we have decoding graphs corresponding to, where all the different errors that could have lit up. And then we add edges and hyper edges to the, respective decoding graphs of the 2 logical qubits every time they do operations with each other. And this allows us to, for example, undo this error propagation by just keeping track of how all these correlations can exist. However, as we do, more and more complex circuits, errors will build in time, because every time we do operations, they're not perfect, and we're going to increase the entropy of the state. And we need to somehow, with error correction, remove entropy. And so here, what we're theoretically studying is whether we can use this correlated decoding to reduce how much we have to do this actually entropy removal. And a key insight here, this is maybe slightly technical, but what's often the case in error correction literature is that every time you do a logical operation, you have to do D rounds of stabilizer measurement every time you want to do error correction. And that's because if you have a faulty stabilizer measurement, you might actually make a catastrophic error. So you have to repeat your stabilizer measurement many times so that you're sure about the measurement result of each ancilla. So you can undo, so you're not fooled by measurement errors of the ancilla. However, once we're doing these algorithms, if you have like a huge code, like a distance 1,000 code, it doesn't make sense that after you do one operation, you need to do 1,000 rounds of stabilizer measurement to remove that entropy that you created into that state. It's just like, this local thing. And this D rounds that we have is really just a bug for measurement errors. However, when we do these complex Clifford circuits, for example, here, then this is what we're studying here is we have complex Clifford circuits between various logical qubits. And these measurement errors that we have will actually propagate deterministically. And because they propagate deterministically, we can actually track them as we go. And what we see, for example, is that by using correlated decoding, we can actually dramatically reduce the number of rounds of error correction we need to do per gate from having to do D rounds that we can get away with like 1 round. It's actually even less error to do fewer than D rounds. So not only it reduces the error in the system by not having to do as many operations, but also speeds it up. We don't have to have as many resources now to do an algorithm. And in terms of the overall cost of doing a complex algorithm, we see that we can actually reduce the space-time cost by, in these Clifford circuits here, by actually using this correlated decoding technique in order to, speed up this error correcting algorithm. Are there any questions here?
You should mention Chen Zhao.
So, and Chen, yes, and Chen and Maddie are really, instrumental in this endeavor. Okay, fantastic. Okay, so I think I have another 15 minutes, right?
Yes.
Okay, I'll kind of flash through some of the rest of the stuff. But okay, these are some of the lessons that we learned experimenting with logical qubits in the lab. And in building logical processors in the lab, one of the things that's really important is that, with these error correcting codes, we're limited in what we can do. In terms of, we can't do all of these universal operations, which I'll kind of mention in a second. But there's also kind of native hardware capabilities that are particularly well suited for doing certain operations. And a really central aspect that we're excited about here is this aspect that we call co-design, which is that, it's hard to do generic error correcting computation, but maybe specific algorithms with specific error correcting codes we can really cleverly come up with in order to reduce the costs of particular algorithms. And now that we're entering this era of doing early fault tolerant quantum computation, these co-designs and looking for kind of clever little tricks is where we hope we can find big breakthroughs where, maybe at first we find it for a small scale problem, but actually maybe some cheat that we come up with allows us to actually, also, we can also apply this trick to large scale problems. That's kind of the type of thing that we're looking for here. So, okay, one of the really big things I swept under the rug in terms of working with error correcting qubits is this challenge of universal gate sets. So error correction codes only have a discrete gate set available to them. And this is very fundamental to the fact that things need to be digitized. You can't just do an arbitrary single qubit gate. So actually it's very different than with physical qubits. With physical qubits, it's hard to entangle things, but it's really easy to do any single qubit operation you want. With logical qubits, it's really easy to do a transversal CNOT. All these different codes can entangle with each other, but it's actually really hard to do an arbitrary single qubit gate, an arbitrary single qubit rotation. So we should be thinking about these systems quite a bit differently. So for these 2D error correcting codes, like the surface code and the color code, they can really easily do the Clifford gate set, like HS and CNOT, but they cannot do non-Cliffords, like a T or a CCZ easily. And this non-Clifford gate is required to complete a universal gate set. And the CCZ, for example, is controlled on both of these qubits being in state 1, do a Z flip to this last qubit. This is a non-Clifford gate. And this is a problem because we need a non-Clifford gate in order to complete a universal gate set, but it's actually even worse than that. We need a non-Clifford gate to do anything which is classically hard. And in particular, the computational complexity, at least in general, grows exponentially with the number of non-Clifford gates that are applied. And state-of-the-art simulators can handle up to roughly 16 CCZs. And actually, in particular, this amount of non-Cliffordness in the state is the so-called magic in the state. And actually, I know I'm speaking to world experts in the JAPI group in terms of kind of all of the various explorations that have been done and kind of understanding this magic quantity. Okay, any questions here about discrete gate sets? Okay, fantastic. Okay, so we want to study interesting circuits with our early fault tolerant logical qubits. And so here what we chose to do is make 3D codes. So 3D codes lose the transversal Hadamard. So again, they can't have a universal transversal gate set, but they do gain transversal non-Cliffords. And in particular, we make these 8-3-2 codes. So it's 8 physical qubits, 3 logical qubits, and it's distance 2. It's distance 2 in one basis, it's actually distance 4 in the other. And it has this really convenient set of logical operations. So it's another CSS code. So these 3D codes can actually do transversal CNOTs. But moreover, they have 3 logical qubits that are encoded in this one block. And it's actually really easy, now that these logical degrees of freedom are all encoded on the same block, it's actually really easy to entangle them because they're already living on the same physical qubits. And we can do this, for example, we can do a logical CCZ on the 3 logical qubits that live within the block just by doing physical T gates. So physical, T gates, 45-degree rotations around the Z-axis of the block sphere is enough to generate logical entanglement between these 3 degrees of freedom, which is actually quite remarkable in this code. Okay, and then using this, we've been able to make up to 48 logical qubits and do 228 logical qubit gates and 48 logical CCZs. Again, people have only previously done 1 or 2 logical operations. And this is the logical circuit that we do here. So each line here is a logical qubit. And in particular, we entangle everything here on a hypercube, partially because hypercube is really fun to say, but also because it's really good at scrambling things. And we're studying here quantum scrambling dynamics with our logical qubits. So we take these, okay, I guess I'm speaking to a bunch of mathematicians. So, we are entangling our logical blocks on a 4-dimensional cube, but each logical block is a 3-dimensional cube. So actually on the physical level, we make a 7-dimensional cube. So we're making 7-dimensional hypercubes in the lab nowadays. And in particular, these circuits map to a kind of class of so-called quantum supremacy circuits. We're not studying quantum supremacy here. We're just studying, complex circuits. And they map to these so-called IQP circuits. Maybe I'll kind of glaze over this. Okay, but we make these really, okay, is this kind of set up clear? We make these blocks, we can do entangling operations within the blocks, and then we can do entangling operations between the blocks transversely. Okay. So, okay, we make these complex states, and now we want to probe them, and what we do is sampling. So what sampling looks like is we make some complex many-body state, we take snapshots by projectively measuring it, and then we compare the output distribution that we get and to the distribution that we're expecting from simulations. And then in order to quantify this, we look at the so-called XCB, which is just a weighted sum. It's our sampling score. It's just a weighted sum between the distribution we measure and the distribution that we're expecting. And okay, this plot is really important, so please interrupt me if it doesn't make sense. So here what we're plotting is the raw outcomes from the experiment. And here, because it's a distance 2 code, we're doing error detection. In the other experiments, we were doing error correction. But here, because it's distance 2, we can only do error detection or post-selection. And we're plotting here the raw outcomes of these logical bit strings that come out of this sampling experiment. And we can see that it already starts to overlap a bit with the theoretical distribution. So showing that we can get, some non-trivial sampling outcomes. But as we increase the amount of error detection that we do, being more and more stringent on which samples we keep from the experiment, we see that the distribution gets closer and closer and closer to that of the theoretical distribution. And it actually gets to quite a high score for these 12 logical qubits of here 0.7 for the XCB, which is quite a high score for this complex 12 logical qubit circuit. Does this plot make sense? Okay. Okay, fantastic. Okay, let me zoom in a little bit more into the data because I think it's quite amazing. So here it's again looking at the same data, and we have these 12 logical qubits, and there's a 2 to the 12 possible outcomes in our 2 to the 12 dimensional Hilbert space. And we're looking at all the different output bit strings. And the orange curve is the theoretical distribution for the circuit that we do. And the blue curve is the data. And what you see is that across this entire Hilbert space, everywhere there's a theoretical peak, there's a little experimental peak that follows. And in particular, as we zoom in further and further, if you track this red arrow, for example, and you track these, these two little features here, or these two really large features here, you can see even down to this tiny little noise floor, zoomed in all the way to the bottom, you can still see the ripples in the theoretical distribution getting reproduced by the, this error correcting code. And this is something that we have, not seen before doing similar types of experiments with physical qubits. And yeah, maybe I'll just kind of leave that there. So the kind of overlap here and how well we can reproduce tiny little features in the data is really, intrinsic to the fact that these error correcting codes are digitized. And so we don't have things like analog, coherent errors on these logical qubits. Okay, any questions? Okay. So, okay, this is 12 logical qubits. We can also go to, progressively larger and larger sizes. So here we go from 3 to 6 to 12 to 24 to 48 logical qubits, and we're looking at this XCB or sampling score. And what we see in all cases is we get a finite XCB, telling us that we're doing successful sampling. And we also see that our XCB score improves as we increase the amount of error detection that we do. And in particular, the error detected XCB that we get, or this post-selected XCB here of 0.1 at this 48 logical qubits with all these complex circuits. I know it sounds quite technical, but the sampling score is actually quite a bit higher, roughly an order of magnitude higher than state-of-the-art previous physical qubit experiments that have been done at a similar scale. And so at the cost of measurement time, because in this particular experiment we're doing error detection, we can really start to use our logical qubits to outperform physical qubits at certain tasks, like here, studying the outputs of this complex circuit. And this is a movie of what exactly this circuit looks like on this logical qubits. So we're going to first, in this first 3 steps, so 1, 2, 3, we make these 3D 832 codes, and then we start to entangle them on higher and higher dimensional structures. And we're making here again hypercubes on both the logical level and physical level. We run out of space here because we can only entangle so many qubits at a time. So we move these qubits into the storage zone and then leave them here where they can preserve coherence while we're doing more entangling operations. And then we do this process all over again, and again make this high dimensional hypercube. And then we entangle this first group here with the last group. And then that's how we do our logical circuit. And if there's anything that you're going to remember from the experimental implementation here and from our talk, is that if you're going to do a circuit like this on the logical level, it does not make sense to have a unique wire for each individual physical qubit in the block. You should have one big wire that does the exact same thing because all of the qubits need to do the same thing anyway. That's the kind of really central takeaway. Okay, any questions? Okay, if not, then I'll just kind of wrap up. Okay, so okay, maybe as one, just 2 more things. So not only can we do things like sampling, we can also do other, fun physics explorations with these error correcting codes. So here in particular, what we're studying is kind of quantum simulations, and we're studying how we can do, fault tolerant compiling, like efficiently studying certain types of quantum simulations with, again, logical qubits now. And one of the things that we did here is we make a complex state by doing the scrambling, and then we want to measure something like entanglement entropy. And we can actually do this by making 2 copies of our logical qubits, entangling them by doing this Bell basis measurement. And then we can measure the entanglement entropy here. And of this fast scrambler, we actually see this really clean page curve by doing this, error corrected implementation, much cleaner than we've been able to see before with physical qubits. So we can already kind of start to use logical qubits for things that, physics that we like to study with physical qubits, but now we can study them in a cleaner setting. We also, for example, here, I know that this group really likes magic. We can, measure the amount of magic that we introduce into our logical circuit. And we see here that as we increase the number of logical CCZ gates, we can use this 2-copy method to extract how much magic we're doing. And we can actually see that we're increasing the magic in the state. And we can also analyze this data in a variety of various ways and kind of probe pretty complex things with these error correcting states. Okay. So, okay, to summarize, so I'll just kind of skip to the end of the talk now. We're making here quantum operations that improve with code size and make surface codes as large as System 7. And here, this correlated decoding concept that Maddie K and Chen Zhao worked very hard on was really important. Then we're doing fault-tolerant algorithms and characterizing our zone processor in various ways. And then studying complex scrambling circuits with these small 3D error correcting codes and doing hundreds of logical techniques. Okay, so the salient question here is, what did we learn and where do we go from here? So in terms of some of the key lessons from our first generation logical processor, the key one that I cannot possibly say enough is that it's the control over single logical qubits as the fundamental units in this processor that has enabled these complex experiments. So if you were to come into our lab and see, for example, this is a diagram that we drew for ourselves when we're doing this GHE state experiment. This is an experiment that's still built and operated by only a few PhD students and postdocs in a university lab. And the reason we're able to do these complex circuits is because we're not programming a complex physical qubit circuit, we're programming a simple logical qubit circuit. Where here, to make this GHE state, we're just thinking about this transversal CZs that we're doing in parallel on all of these blocks. So that's really the central takeaway, is that of efficient classical control. Another one, in terms of a practical lesson with this correlated decoding, is that once we start to study algorithms between these logical qubits, it doesn't really make sense to draw lines at where logical qubits end or begin. It makes more sense to think about them together as a whole, and that's where this correlated decoding concept comes from. Another interesting fact is that logical qubits are not actually literally qubits, they're many-body systems, and they can behave in funny ways. So one example is that, when we make Bell states and we study their fidelity, it's actually quite a bit different than how it works with physical qubits. There isn't something like a logical span and a logical gate fidelity. It's something that's more complex than that. But also we get pleasant surprises, like we get inherently digital operation, where even when the fidelity of the system isn't perfect, coherent errors in these logical circuits are highly suppressed. And I think that there's genuine examples here where logical qubits can already be used to outperform physical qubits at various interesting problems. This discrete gate set is a challenge because, now if you have a specific algorithm that you want to realize, it isn't necessarily easy to realize it. However, if you flip that on its head, it can actually be a real opportunity, because if you find a specific algorithm that actually can be realized with something close to this discrete gate set, it's actually one of the few unitary operations the system can even realize. So it's actually something that it can realize really precisely, because it's one of the few places in Hilbert space the system can even touch. And here, actually, I think that there's many open mathematical questions of how to do algorithms with error correcting qubits that are quite unexplored. And I think it'll be really interesting to kind of think about these various things across communities. I think this is a place where mathematics can be extremely powerful. And I think there's going to be many more opportunities here for near-term studying early generation logical algorithms in the lab. So that's what I would call kind of our early generation logical processor experiments. Going into the future, we would also like to continue to make these systems larger. And something that's quite exciting with neutral atoms is that we're charting a path to getting to what I would describe as these medium scale error correcting systems, where another key step will be, like we talked about with the correlated decoding, a really important step will be to remove entropy as we do that algorithm. It's one thing that we're working on. We believe that essentially by just increasing laser power, we can scale our existing techniques to the scale of roughly 10,000 atoms and get our 2-qubit error rates to the scale of 0.1% from the current error rates of 0.5%. There's also some other important technical things here. But what I want to highlight is there's so much various work going on throughout the neutral atom community across many different groups, and a lot of really exciting progress is being made. And I think in the coming years, if we're really able to pull it off and really be able to combine these various insights from all these various groups, then there will be a path to being able to do something like having 100 error correcting qubits that can do 1 million operations without an error. And just with these various parameters that are achievable in the near term. And that's not something that immediately is going to allow us to solve large-scale problems necessarily. But this medium-scale device will be a radically different type of quantum computer than we've ever had before. It'll be a quantum computer because circuit evolution is not limited by depth anymore, because you can just make extremely small errors. If we're able to build these things and study them in the lab, it's going to really change the way that we study quantum computation, and also even just the way that we interact with quantum mechanics. And I think it's going to be a pretty exciting thing. And this also starts to open some key theoretical questions that, again, I think mathematics can be really powerful for answering. So one is, what algorithm should we even study with 100 logical qubits and 1 million logical gates? It's quite a bit of a different regime than we've previously thought about before. And also, how do we structure these algorithms for doing efficient implementation, similar to how we found here for doing specific scrambling or sampling circuits, a really efficient way with these 3D codes? What, for a specific algorithm, how can we do this fault-tolerant compiling to find inexpensive ways to realize particular algorithms? This is a really big open problem. Again, I think mathematics is really useful for. This is my last slide. So that's kind of getting into these medium scale error correcting devices. We're also really excited to think about these large scale error correcting devices that, again, we're thinking for these really large scale problems. And here we need things on the scale of millions of physical qubits, creating logical qubits that have errors on the scale of 10 to the minus 10. And my honest assessment of this is that this is still quite daunting and still something that's quite challenging for us to realize. And we definitely have avenues that we're exploring here from things such as LDPC codes, which have dense encoding rates, also different ways of trapping more atoms, being able to maybe connect different neutral atom modules together with photons. So we're definitely exploring various things here. But the reason I really want to emphasize that this is not solved and we're still working on it is that we're really looking for as many breakthroughs as we can get, both in the hardware, but also in terms of the theory, and kind of finding cheaper and cheaper ways to program and reduce the algorithm cost. And at least in my personal belief, the experimentation we do with these early generation logical devices will probably dramatically reshape the way that we actually think about these large scale devices. Okay, that's the end of my talk, and I'd like to thank my amazing colleagues. And I only just added in the correlated decoding slides, but yeah, Shen should also be here. Yeah, thank you. Yeah, thank you.
Well, thank you very much. Thank you. Wow, it's a really beautiful overview. And I'm sure that there's a lot more questions, even though there were many. So let's go. Maybe there's questions online, because we've had a lot of local questions here. Well, if nobody speaks up, would it be helpful to think about qubits or more than two-state systems?
I think so. Yes, I think it is. And so to me, it's still an open question whether like qubit error correcting codes can have certain properties for certain algorithms that can be much more inexpensive. And if the answer is yes, then I think that would be amazing. So I think as far as I'm aware, this is still a pretty nascent area of study. People haven't explored it much. But I think it would be really interesting to understand what the kind of fundamental no-go theorems are, or where the fundamental kind of advantages are. I think it's not clear to me. But I think it would be really interesting.
Is it easy to do it in the lab?
Yeah, we definitely have ways that we can make more than 2 levels. Like we have in our ground state, we actually have 8 levels. We use 2 of them that are particularly convenient to use as our qubit state, but we can in principle use more levels if there's a really good reason. Yeah, I think qubit error correction is a really interesting question.
So earlier we had this plot where you mentioned the spell magic.
Yeah.
So can I ask, were you introducing T gates to kind of inject magic in your circuit? You were?
No, so actually, we were doing, it's actually kind of amazing. So on the logical level and the circuit that we measure, we're doing CCZs. So we do logical CCZs. Here's a remarkable fact. The way we make these logical CCZs is with physical T's. We do 8 physical T's on this error correcting block. And on this encoded 3 degrees of freedom, we make a CCZ.
Okay.
Remarkably, okay, this is going to be a side tangent. Remarkably, we do this 2-copy measurement by taking these 2 copies and doing this Bell basis measurement. That's a logical 2-copy measurement. It's also a physical 2-copy measurement. And actually, we measure the same magic on both the physical level and the logical level, which we can simultaneously analyze. Yeah.
So let me ask a follow-up question. So you said you what, like 8 T gates per
CCZ, yeah.
Okay, so overall, what is the total number of T gates that you had to look at for the?
That's such a good question. Okay, so now let me rank, because you gave me the soapbox to do this. Okay, for our really complex circuits, like 48 logical qubits, we have like 400 T gates or something like that, because we have 48 CCZs, and each of the 48 CCZs is composed of 8 T gates. Okay, so like for our really complex circuits, we're doing hundreds of T gates. Okay, but then now let me make another comment, which is that the best unitary decomposition of a CCZ is 7 T's and 60 knots. Here we do a CCZ by doing 8 T's and 8 C knots. Like we do a CCZ by doing 8 T's every time we do this transversal C naught. So it's actually very close to the best known unitary decomposition, but it also has this error detecting property. So this 8, yeah, so it's kind of amazing.
Last question.
Please.
So, but roughly 400 T gates.
Yeah.
How many qubits were you doing this on?
So it's 48 logical qubits and 128 physical qubits.
Did you find that the measurement for the magic was roughly efficient? Like you could do it in a reasonable amount of time?
So the magic measurement we did on much smaller systems. And I don't remember the exact scaling off the top of my head, but I think it's not exponential, right? I think it's like polynomial for this Bell magic scaling, but I would have to review.
Maybe I can talk about, because we're studying a similar kind of thing. I'm wondering if it's a vision.
Talking more offline sounds awesome. Yeah, yeah, I would have to, yeah, we're utilizing this, yeah, let's talk more separately. Yeah.
I have a question. So you use a distance 2 code.
Yeah.
3-2 code. So actually you cannot do correction. You can only do detection and
That's right.
post-correction.
That's right.
Do you have any like future plan to use some longer distance code that you can do correction during the time, not just do post-correction?
Yeah, so definitely yes. And also to clarify, so in the first 2 experiments I showed, the surface code and the color code, there we were doing correction. They just weren't 3D codes. We also can make a higher distance 3D code, just then we're using more of our qubits to make an error correcting code, so we can just make fewer logical qubits. But yeah, we definitely have plans to do error corrected non-Clifford operations as well. Yeah.
And then another question is like when you have T in this like 832 code, I mean CCD, by applying T on each qubit, you also do post selection when you have the errors on this T.
Could you say it one more time?
I mean, when you have this like CCZ gate, this CCZ gate by applying T on each physical qubit.
Yeah.
You also do post selection when you have to detect some errors on this like CCZ gates or maybe and then I just want to know like how can you do error correction or error detection on a non-Clifford gates of this kind of thing.
So let me see if I understand your question. So when is the error detection or error correction actually happening?
Yes.
Maybe if I understand correctly. So for example, let's imagine we do a complex circuit that's composed of many CCZs and many C-naughts.
Yes.
And there's, one error in the system, then it'll still be fault tolerant. So if that error happened whenever during the circuit, it won't actually create a logical fault. And then by the time that we get to the end, it'll still be detectable and we can still post-select it away. So even if it went through many CCZs, does that kind of answer the question?
Yes.
Okay.
Okay. Yeah. And maybe my last one is
Yeah.
like about this coherent decoding.
Correlated decoding, yeah.
Yeah, because so it just reduces the wrong you need for measurement to correct
That's right.
one logical error.
That's right.
Okay.
Yeah, so it has 2 features. So one is that it picks up for correlations between the logical qubits, and this allows us to, improve our fidelity. We're using more information to undo the errors in the system. So that's one big feature.
Yeah.
Here's another big feature, is that because we can keep track of how measurement errors propagate between logical qubits, it actually now is not catastrophic if we have a measurement error before we do an entangling operation, because it propagates in a deterministic way. And as long as we just keep track of that, then we can undo that. And so actually now as we do a complex circuit, we're injecting entropy, but we only need to do, roughly 1 round of error correction every time, we introduce entropy, just to remove that, newly added entropy. And we can just track the measurement errors as they go by doing the correlated decoding technique.
Yeah. So every time you apply this transversal C0, you actually correct that. And then, but the wrongs are reduced to just 0.1, as you said.
Yeah, that's right. Yeah. And so you might have had a measurement error right before the C0.
Yes.
But actually if you track it, then it's okay, because you'll later figure out that it was a measurement error.
So I think we should thank Dolev again for a really beautiful overview.
Well, thank you.
There's going to be a lot of private discussion going on after this talk, and we look forward to your coming back and telling us about the next series of results. Thank you.